Alright guys, so welcome back. Let's go ahead and finish part 2 of this chapter. Okay, if you haven't yet, make sure you go check part 1 in the series. We cover the first half of the chapter. And in this second half, the second half should go by faster than the first one, right? Because if you take a look up here in the upper left-hand corner, you'll see we're on page 42 of 76. So this should go by faster. I'll get you out of here, get you on your way a little bit quicker. And again, remember, go through the slides with me here. Go through them on your own. Check to see if you feel comfortable, if you understand, what we've discussed. And if you need a little bit more depth, then go ahead and hop into the textbook and read a little bit deeper, read a little bit more, from the sections. Okay. So I'm providing slides as a way to help guide the discussion, but also to guide what you need to know about, because remember, the textbook goes into a lot more depth sometimes than it needs to for our purposes. Okay, so when we left off last time, I had talked to you about 4 different approaches to designing an architecture for an agent. Okay, so that's where we were about to get started. So I'm going to go through these with you really quickly, and then I'm going to talk a little bit about their components. We're going to look at a little bit of pseudocode, going to look at a little bit of a picture for you. And then we'll talk about how some of those components might be built. Okay. And there is a link, should be provided on Blackboard now, to the source code repository. So you can go check that out and see actual implementations of each of these things. Again, in either, I think there's Python's there, C# is there, there's Java implementations, and Lisp, right? You'll write some programs in Lisp later on in the course, but review that stuff and feel free to use it at will. You have my explicit permission. You're not cheating by taking that code and modifying it for your homework assignments, right? So I highly encourage you to do that so you can see some of the implementations here, and then try to tie it back to what we're discussing here. And also remember, you must be able to understand the pseudocode. Check the appendices at the end of the textbook that walks you through the basics of the pseudocode. I'm going to hold your hand for the first few chapters, but eventually I'm going to say, okay, it's your turn now. You're going to have to, I'm not going to go into as much detail on the pseudocode. Okay? But anyway, so first up, we were talking about simple reflex agents, model-based reflex agents, goal-based agents, and utility-based agents. Okay, so this is talking about 4 different approaches to the architecture, like I was just saying, for creating your agent, or more precisely, programming the agent function, which makes up the agent program, right? So the implementation of that agent function is going to make up your agent program, which is going to control your intelligent agent. Okay, so simple reflex agents. This is the simplest kind. Okay, and so for the homework assignment for this chapter, you're going to have to design a simple agent, right, to operate within a certain environment. Previous video I said, hey, you could use this table. You could make a table-based agent, right? Well, here's another approach. You could write an agent function that basically is just made up of a bunch of if-else rules, right? So, you can test to see if something's true about the environment that the agent finds itself in. And if that's true, then you're going to produce some kind of action, right? That will be translated or transferred over to the actuators, which is going to cause the agent to behave a certain way within the environment, thereby modifying its environment. So this right here is an example of a simple reflex agent for that toy problem that we outlined in the last video, the vacuum world. You remember 2 states, space is dirty or it's clean, and then the vacuum can be in one or the other spaces, right? So the way we can read this function, okay, the simplest kind of agent, is that you take a particular percept, and so in this case, you'd have the location of the robot, the vacuum, right? And then also the status of the square. Is it dirty or clean, for example, okay? So, based off of that input to this function, you're going to have an output that is the action that the vacuum cleaner should take. So here you can see that we've got hard-coded in pseudocode that looks like, an if-else structure. That's what it is, right? So what this is saying is, well, if you're giving me a pair of values, right? The location of the vacuum and the status of the square that the vacuum's in. So if the status of the square is dirty, then return suck, right? So by doing that, we've mapped dirty status to suck, right? Did some dirty, doing some sucking, okay? And that is the idea behind, one part of that function, that agent function, right? But what if it's not dirty, right? If it's not dirty, if the status is not dirty, then the square is clean. So if the square is clean, then you got to move left or right. The vacuum has to move left or right. So then that's where this else if comes in, right? So it's not a dirty square, right? So then we kick down. And you can imagine how you code this. Think about translating this into C++ or Python. A lot of the homework you're going to do is that kind of thing, okay? Otherwise, if your location is equal to A, right? So if you're in the A square, then return right. So by doing that, you're saying, well, if it's clean and the location is A, then the vacuum should move right, right? So instead of a table like laying this all out, we're using logic. We're using a decision structure, okay? Otherwise, if the location is equal to B, then return left, right? So if it's dirty, just suck. That's what you do. Otherwise, if it's not dirty, are you in A? If so, go right. Otherwise, go left. That's it. So with this type of an agent, all it's doing, okay, it doesn't have any memory. All it's doing is considering the current percept, what it just perceived. Everything leading up to this point doesn't matter. Okay, this particular agent just goes, what did I perceive about the environment? Okay, I'm going to make I'm going to choose an action. I'm going to make a decision based off of that one percept, not an entire sequence of percepts. Just what you perceive about the environment right now. Now, for our toy world problem, it's sufficient. Okay. So that leads to what's the benefit of that? Much shorter agent program. You don't have to use this huge table. Okay. So you just are using if-then logic. Whatever language you're implementing it in, it's just as long as it's got if-then logic, cool. Try to detect something about the environment, and then if you do, or based on what you detected, I should say, choose a reaction. So this is known as a condition action rule. So here's an example for this self-driving car. Okay, here's that if, then, or if, else, if then, and then if you do an else if in here also, chaining it together. But it's just, if this is true, then do the other thing, right? So Java has logic like that, structures like that, C++, C, Python, Lisp, whatever, right? So here is your condition, and then here's the action that should be taken. If the car in front is braking, then initiate braking, okay? All right, so figure 2.8, we had pseudocode that hard-coded all of that in, okay? And so, for a simple reflex agent, cool, okay, great. Right? But if you want to make it a little bit more modular, if you want to make it a little easier to update, if you want to be able to switch out behavior, write it more of a modular fashion where you have a condition action engine, okay? And that engine can be programmed for different situations, different environments. So you might have like your robot, okay? And then depending on where that robot is going to behave, or where it's going to be performing its duties, maybe there's some firmware in there, and then you flash update the firmware, with a different condition action engine module, so that way you can customize how that particular agent's going to behave. Okay. All right. So here's the schematic diagram, the picture I was talking about. Right. So you got your environment, you got your agent, and there's going to be components of that agent that are going to be working together to control that agent. Right. So sensors sense the environment. What's the world like right now? Okay. Now, based off of that condition action rules engine, right? You take a look at what the world's like now, try to match up, a condition with an action, and then that'll tell you what action you should do now, which you then pass off to your actuators, which then updates your environment. So that's pretty simple. Okay, so here's something a little bit more generalized, right? That very first example I gave you was if else. So here is a more generalized version that follows from this diagram, the schematic. Okay, so what you have here is a function in this pseudocode that says, all right, well, you're going to have some function that's going to interpret your input for you, right? So maybe you're, like I said, we're looking at a function that's more generalized. It's not, this is a more abstract idea, right? More abstract way of looking at it. So percept comes in, action comes out. So what's persistent? Rules, right? So you've got a set of condition action rules, right? That's going to be available to your implementation of the agent function. And so this adds, in this discussion, what we're doing is we're adding a function that's called interpret input. And so what this does is this function, okay, this component will take that percept that was given to the agent function and then interpret that percept to then be able to report, okay, well, this is the current state that the agent is in. Okay, this is the state of the environment. Based on what I've perceived, this is the state that I find myself in. Okay, and so then you have another subcomponent, and we're just modularizing, okay, in this generalization. So we got another component, a rule match function, which takes the state that we had just identified by using the interpret input subsystem, subprogram function, right? And then taking that persistent rule set and say, okay, well, identify for me which rule I need to work with, or what rule is applicable to this particular situation. Okay, so we've identified the rule, given a state, and the set of rules that are available to this agent. Okay, now once you've done that, then that rule, remember there's the action portion of that rule. The condition portion is what's being used by the rule match function or subsystem or subprogram to identify which rule and therefore which action attached to that rule should be taken by the agent. So that's what this is saying right here, right? There's an action that's part of the condition action rule, and so that's the action you should take, so return it, right? So what this is showing us is that if you're going to, in general, understand what's going on, there's some set of rules, of condition action rules, okay? The agent has to interpret the percept that it's given to identify what state it finds itself in, what state of the environment finds itself in, and then you have to figure out which rule matches that state, so then you can retrieve the action that the agent needs to take, and then you can return that action, right? So again, this is representing the agent function, right, that you will have to implement in your agent program, which when combined with computer hardware or with a robotic hardware or whatever, is going to control your agent, right? It's going to be the manifestation of your agent. Okay, so many different ways you can implement that abstraction. I've been trying to stress that. Okay, different languages, how you actually write the if-else condition action rules. Is this going to be some kind of an array? Is it going to be a vector of some kind? Is it going to be some kind of dictionary? Whatever. Okay. Are you just going to have, a chunk of code that's a bunch of if-elses inside of this rule match function, and maybe a bunch of if-elses inside your interpret input function, right? So we're just breaking up so we can identify easily all of the different pieces that belong to this. Okay. Now, can be implemented many different ways. So what's the biggest pro? It's easy, it's simple, it's easy to understand, it's easy to grasp, and if the environment is simple enough, you can write enough rules to deal with that environment, all the things that you could perceive. Okay, so good, that's good. Now, what's the bad? The intelligence for it is limited, right? And um, there's only so many if-else rules that you can write. Kind of like the table-based agent, there's only so many entries in your table you can have. Okay, the agent itself has to work in a fully observable environment. Why? Because it has to perceive something and use that percept to find a matching rule to identify the types of actions that it's going to take, in response to that percept. Okay, so um, a self-driving car has to make a decision based on one image frame. That's kind of bad, right? I mean, because if I mean, as an example, right, that self-driving car, if it's using this type of agent, it just sees, a car in front of it. All right, well, what do I do since I saw a car, right? I mean, is that car slowing down? Is it speeding up? Is it turning? What? I mean, it's just, you only get to see the one percept, and then you have to make a decision. So you're kind of limited in your options there. The vacuum robot itself could end up in an infinite loop. I mean, if you remember when we looked at that hard-coded if-else rules, right? If not dirty, location A, go right, right? And so then the next instance of time, you run through your agent function to figure out what you're supposed to do. Well, then you're in the right square, right? You're in square B and it's still clean. So what does that tell you to do? What does that decision structure tell you to do? Well, then go left. And so you're just bouncing back and forth, bing, 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 bing. So that can lead you to an infinite loop. Okay. Let's see here. All right. So another example, if the um, agent is lacking in the location center, right? If you don't have the right type of sensors to sense the environment, then that would mean that you have an environment that's only partially observable, right? So you don't know which location you're in, but you can only tell if you're dirty or clean, right? If that's the case, then that robot might run into the vacuum cleaner, might run into a wall, and it's like, well, I can't tell if I'm in this particular square or that square, so it can't make a decision about whether it should go back to the left, go back to the right. Okay, so you can use a little bit of randomization, building that in, so that way you can break out of loops, right, where you're just bouncing back and forth, left, right, left, right, left, right, left, right. Or in a partially observable environment, you hit that wall, it might just keep banging against the wall. So every once in a while, every 10 actions or so, you could just flip a coin, right? And that might be able to break you out of that endless repetitive cycle. All right, so let's talk about model-based reflex agents next. These add a little bit of complexity, but what they allow you to do is take into consideration how the world works and gives the ability to perform in a partially observable environment, right? You might not necessarily need to know or be able to sense everything about the agent's environment for that agent to be able to make decisions. Okay, so what's the best way to handle potentially a partially observable environment? A agent working within that partially observable environment, right? Maybe it doesn't have all the sensors it needs, or maybe one of the sensors goes down or breaks or something, right? So what do? Keep track of the part of the world that you can't see at this particular moment, okay? So you're the agent is kind of keeping track of, in its head, a sort of internal state that depends on the percept history, right? So think about if you're a person, right? Well, you are. Duh, what am I saying? Think about you walking or wandering around your house, okay, during the daytime, or maybe you're at night and the power goes out, okay. Well, you've been wandering around your house for however long you've lived there, okay. And if you haven't moved any of the furniture around recently, then you kind of have an internal state, an internal map in your head of where things are laid out. So you suddenly lost a sensor, so you're no longer able to perceive things visually, right? You're kind of blind, okay, because it's dark. but you can remember where things are because you perceived them in the past. So you have an internal state of where you're at, right? You were just walking from the kitchen towards your bedroom or whatever, and the power goes out. Oh well, I was just in the kitchen, then I went into the hall. All right, okay. So I must be in the hall now. Okay, so internally you can figure out where you're at because you remembered where you've been. Okay. All right. So another example of this, the self-driving car. Okay. Now you have a single picture of the car ahead of you. Okay. And from one instance in time, the self-driving car says, "All right, I just took a picture. There's a car." Okay. And then the next, I don't know, second, next split second. Okay. The next percept reflects a change, right? There's a change. So previous split second, car in front of you, brake lights off. Next split second, you get a new percept, okay, and the brake lights are on. So you kept a memory, right, of what just happened, right? So you now have the ability to make a comparison, to compare changes, right? No brake light, brake light. Oh, well, maybe I should stop. Okay, so this type of approach is going to require that internal state, right, what you think about where you're at right now, needs to be able to be updated, right? The ability to update your opinion of what the state of the environment is at this particular moment. Okay, so how? The agent has to know or has to have information about how the environment can change without the agent's knowing, or how can I put this? How the world changes without the agent. So how does the world behave, right? To take the agent out of the equation for a second, right? How does the world function? Okay, so the self-driving car, what happens in the world? You have to be able to know that brake lights mean stopping, right? So the agent has to have information about that. But it also has to have information about how the agent can impact the world, okay? So you have to have a situation where you can update that internal state, okay? Information about how the world changes, regardless of what the agent does, but also how the agent can impact the world, how it can change that environment. So some examples, right? If you speed up, that means that you get closer to a car, right? It doesn't matter who you are, okay? Turn the wheel left, car goes left. Doesn't matter who you are, if you're the agent or if you're something else. This is the reality of the world in which the agent is operating within. And by world, I mean environment, okay? If the car is in motion for a certain length of time, then the location of the car changes. Okay, you're going to go forward a certain distance based off a certain. You're learning about the physics, or you have to have a little bit of understanding about the physics of the world. Okay, that agent has to have some understanding about that. So the knowledge that describes that world, right, that the agent has to be aware of, that is known as a model of the world. Okay, a model of the world. What you know about the world to be true. Car can move a certain amount of distance, a certain amount of time. Turning left makes you go left. Turning right makes you go right. That sort of thing. Okay, so agents that take this kind of approach, where they're keeping an internal representation of the state, right? Keeping track of previous states, the ability to compare one state from the other, right? To be able to deduce where you're at right now, or what decision you need to make, what action you should take. Right? This is in keeping track of this model, this knowledge of how the world behaves. Agents that use this approach, they're known as model-based agents. All right, so a little bit of math here for you, a little bit of an equation. So what is an updated environment, right? Or the agent's um, opinion of the updated environment, or how it thinks about what it means for an environment to be updated. Well, you have the original state of the world, right? Your knowledge or the agent's knowledge about how the world can change. I remember we were talking about knowledge of the world's physics. Okay, how could the world change? Well, based off of what I know about the world right now, how it possibly can change in general, but also how my actions can affect the world, right? So what impact I can have on the world as an agent. Okay, so one possible updated environment could be what it was, how it can change without me, and how my actions can change the world. Okay, so based off of the rules that I've been equipped with, the condition action rules, and how the environment can change, I'm going to make a decision. So those are going to be kind of my two inputs. Okay, what are the rules that I'm equipped with? How the environment can change. That's those two factors are going to determine how I make my decision. Okay, so here is a schematic of it, right? Another picture. So got my environment. I sense something in the environment. Okay, and what the world is like now. Okay, what I think the world is like now is going to be based off of the original state, right? That internal model of the state, that internal state, right? What I think the world's like, how it could change, and how my actions can impact the world. Okay. Now, what should I do with that information? What should I do? What should my action be? What's the state of the world now? How can it change? What can I do? That tells me what the world is kind of like right now. So, based off of that, right, I apply the condition action rules that I am equipped with, and that's going to inform my decision. Okay, so how I understand the state to be, how it behaves, what I can do to it. Right, that's going to say, well, what could the world be like? Okay, now what the world could be like based off of those three factors. Apply my rules. Remember, the condition action rules tell me what action I should do. Okay, so based off of what the world is like, match up against a rule for that, and then that'll tell me what action I should take, and therefore control my actuators, which will then update the environment. All right, so the key part of this, right, of this agent function, of the program that would be implemented, is adding this update state function. And that's going to take all of those variables we just talked about to figure out what the updated state could be, right? So model-based reflex agent, you get your percept. So what's persistent? State, the agent's current conception of the world state, what it thinks about the world right now, okay? Model, a description of how the next state depends on the current state and action. So those are the physics of the world, how the world could behave based off of how it works without me being involved, without the agent being involved, and how the agent making a decision could impact that world. Okay, so you got your rules, and then the most recent action that has been taken, right? So the update state function takes the state, that action, the percept you just had, and then the model as we just described it, and then that produces a state which you then feed into, right? You can think of it as like a tentative state, a state that could be, okay? Pair that with your rules, and then that's going to identify your rules table, and that's going to, your rules table of condition action rules. That's going to identify a rule for you, which you then extract the action from, which you then use to drive your actuators, which updates the environment. So really, if you compare this to what we saw before, right? What did we build in? What's added? Okay, because remember, we were interpreting the input before, but we've expanded that. So in addition to the rule match, right, we are considering what the state could become, and then based off of what that state could become, we match that with our rules, and then that tells us an action that we should take. Okay. All right. So a self-driving car can't see behind the car in front of it, but it can guess why it's slowing down. Okay. Where'd that guess come from? The update state function. Okay. So has to make a decision. Brake. Stop. Okay. All right. So goal-based agents. Sometimes the environment isn't going to give you enough information. It's not sufficient on its own for the agent to be able to make a decision. Sometimes the agent needs to be guided, right? So one form of guidance we talked about previously was using a performance measure. Another type of guidance is giving the agent a goal to try to work towards. So goal-based agent is what we're talking about. So self-driving car, where's it going? Well, tell it. Tell it what the goal is. Well, this car should take you to the mall. This car should take you to your doctor's appointment. This car should take you to San Francisco, Pier 1 or something. Right? So you take that goal, you combine it with the model, the knowledge of how things work, how your actions, and when I say I'm talking about the agent, right? How the agent's actions can impact the world. Combine those two things, and then that drives the decisions that the agent can make, or that the agent will make, all trying to reach that goal. All right? So sometimes those choices really going to be easy. Sometimes really complex. And so as we move on in the course, we're going to look at some algorithms that can help flesh out how those decisions are made. Okay, so what are those algorithms going to revolve around? Searching certain types of data structures. Okay, we're going to see that in chapter 3, the very next chapter. Okay, and also planning. So search and planning, these are subfields that are based around studying the best way to find sequences of actions needed to reach your goal. Okay, so what we're going to see, just a little preview of chapter 3, is that we're going to be building these decision trees. Okay, so think of like a binary tree where each edge in that tree represents an action. Okay, and a leaf is a goal. Okay, and the root node is your start state. Okay, and each node represents a state that you transition through, and each edge connecting those nodes represents an action that gets you from state to state to state to state. That gets you to your goal. Okay. All right. So as you're traversing through that tree, right, you're moving from edge to edge to edge, and that provides your sequence of actions. If that makes sense. It might not make sense just yet. Don't worry about it too much at this point. We're going to go into that in detail in the next chapter. All right. So reflex-based agents, they have a mapping of percepts to actions. We've talked about this. Okay, goal-based actions lack this, right? And they use more of an approach that requires reasoning. Okay, needs logic. Instead of just saying, all right, percept, choice, percept, choice, percept, choice, percept, choice, right? By choice, I mean percept, choice, action, right? The combination of that percept and that being mapped to that action results in the choice, right? So it's purely mechanical, right? I perceive this, I do this. As an agent, I perceive that, I do this. Okay, that's it. Reflex, instinct. You can even think about it as instinct. There isn't really a whole lot of thinking there, really, when you think about it. You perceive A, you do B. That's it. Okay, and then if you have enough rules, then you can get the agent to behave in an instinctual way, right, on a fundamental way. You can make it rational if you account for all the different rules. So goal-based agents, they don't rely on that. Okay, they use more logic, more reasoning. Okay, and we're going to take a look at agents that are more reasoning based, and so that's going to drive our study of first order and propositional logic. So that way we can understand how they can use logic to make those decisions, to reason. Okay, so for example, to reach my goal, I had better stop before smashing that car, right? It's not so much about I see car stop, therefore stop. Right? It's like, well, if I want to get over there, right? If I want to get to San Francisco from here, and a car appears in front of me, I should probably stop. That's probably the best route for me. It's not just automatic. I see car, I stop. Okay, it's more nuanced than that. It's more sophisticated. So, goal-based agents, they become a lot more flexible. Okay, because of this ability to reason, because it's more closely um, matching thinking, right, than just reacting. Less efficient. Okay, less efficient because you can imagine that if it's not algorithmic, if it's not instinctual, if it's not just A, B, there's more going on. There's more work that has to be done. Okay, and the nice thing, a nice pro about them, I mean, to that con, they're less efficient because there's more work that goes into reasoning, is that they can learn, right, from past events that they went through to modify their decisions in the future. Okay, so like I was saying, those reflex-based agents, they're just sets of rules. Okay, and as conditions are changing, you'd have to rewrite those rules. You'd have to reprogram it to deal with, different scenarios for that agent to be able to deal with different scenarios or different situations that crop up in the environment. So goal-based agents more flexible, but takes more resources to actually reason. Okay. All right, so let's move on. Utility-based agents. So a lot of times you need decisions that are made that are of a higher quality, that are more sophisticated. Okay, you want to make better decisions, so you have to be able to grade one decision against another, right? So you might design an agent that's controlling a self-driving car, the AI for that, and you might just say, well, start in LA and get to Maine. Okay, now you may have that agent reach its goal. It might get from LA to Maine, or from San Francisco to Maine, wherever it starts from, right? Someplace in Maine. Okay, it gets there. But did it get there in the shortest time? Did it get there using the least amount of fuel? Did it get there traveling the fewest miles? Maybe that matters, right? So a bunch of lesser quality decisions, right, where it takes the longest route to get there. Okay, you reach the goal, but they weren't making the best decisions to get there because you wasted a lot of fuel or whatever. Okay, but what if instead we could have the agent reach the goal in a more efficient way? Well, the decisions it makes to improve its efficiency, those are higher quality decisions. Those are better decisions. So what we need is a way to measure the difference between the lower quality decisions, the poorer decisions, and the better decisions. Okay, so the differences between a poor decision and a better decision, you could say, is the difference between one type of state and another type of state, right? Because an agent is moving from one state to another based off of a decision. Okay, so if based off of one decision as opposed to another, one decision leads to state A and another decision leads to state B, okay, the differences, or the difference in the quality between state A and state B, okay, between the poor state A and the better state B, that is a measure of utility. Okay, we call that utility. So it's a performance measure. Okay, it's a performance measure that is measuring the outcome, the benefits of one state versus another. So if my self-driving car is leaving from San Francisco and it wants to go on I want it to take a straight line to Maine to be as efficient as possible. Right, moving from California to Nevada, right? Going to Nevada would be a better state literally, right? Having the car in Nevada is a better state for that car than having that car move to, say, Oregon, right? Because if Maine's over here, California's here, Nevada is in between California and Maine. Oregon, not so much, right? Because Oregon's going the wrong direction. So a utility, the difference in um, the value of Oregon versus the car being in Nevada, we're talking about a difference of utility. It's a better decision for the car to go to Nevada than it is for it to go to Oregon. Okay? All right. So by having some kind of a performance measure, by grading that utility, we can then come up with better state sequences. Right? In this case, again, I'm using states, right? The sequence of going from California to Nevada to Utah, then to Colorado, then to, and so on, right, would be better than a sequence of states that was California, Oregon, Washington, Montana. You see what I'm saying? So we can use a measure of that utility to try to guide the agent in a certain direction to make it have better, higher quality decisions. Okay? We can make it a little bit more intelligent. That way we can score in an objective way, which outcomes are better than the others. So this performance measure manifests itself, right? Shows up in our agent function and therefore our agent program through what the textbook refers to as an agent's utility function. Okay? So that utility function can evaluate the decisions that were made and provide a score. And if that utility function, the score that it provides, and some external performance measure, if they agree, right, then you can say that an agent was rational. It chose the most rational course, right? So if every time the agent chooses a state that's closer to Maine, we say like +1, okay? And every time it chooses a state that's further away from Maine, we say -1, okay? Every time it moves further away from Maine, then there's a deduction in the utility value, right? That overall score. Now you could say that if it takes the fewest states to go from California to Maine, maybe, I don't know how many states that is, maybe there's 12 states, right? So the best score then would be 12. That would be our external performance measure. We could say, okay, well, if you only pass through 12 states, 12 points, that's perfect, right? Now, if based off the decisions, the utility function reports an overall total score of, I don't know, 27 or something, right? Or, some value that doesn't line up with that, well, then you can say, well, it's not irrational, right? It chose a less rational course. Okay, so there are many different ways to quantify what's rational, and this isn't the only way. But lots of flexibility are there because you can tailor the values, the scores that are produced by that utility function. Okay, and you can also use the utility function to help improve the learning that the agent is going to have to do, or that it will be doing. Okay, so the utility function also provides the ability for an agent to say, okay, well, let's talk about the different types of outcomes that I could have if I choose A or B, and then try to figure out, well, which one's more desirable, right? Which one's better? Because you can score. You can score the state that agent is going to end up in. Okay. So now remember, right? It's possible to create rational agents, but it's not possible to create perfect agents. So a utility-based agent, we can say that it's rational if it makes the decisions that lead to actions that are going to maximize, that are going to give you the best score, the best expected utility of a set of action outcomes. So it's rational if it makes the decisions that go through all of the states that have the best value that it could possibly have. Okay? Now, threw a lot of stuff at you, a lot of terminology. It seems kind of simple, but we're gonna dig into it. Okay? And in the next chapter, we're gonna be looking at algorithms that heavily rely upon the utility function to guide the decisions that the agent is going to make. Okay, so choices can be assigned values based off of the overall value of the states of the environment that results from the action that the agent chose. Okay, so current state of the environment that the agent finds itself in plus an action that it chooses to make results in an updated state of the environment. Okay? So perceive the current state that you're in based off of that perception. Make an action. Okay? Current state plus the action decided leads to a new state. Now that new state can be evaluated according to utility function against other potential states that were the outcome of other actions. Okay? Now the difference in those utility values can determine what's more or less rational. Okay? If you have any questions on that, give me a holler. All right, so model-based, utility-based agent. So what did we add? Okay, what did we add? Okay, so we know what the world is like now. This is similar to what we saw with the model-based agent, and that's impacted based off of the existing state, our model of the world, how the world can evolve, what my actions do, how it impacts that world. Okay, and then we can say, take it a step further and say, well, what will the world be like? How will it change if I do A? Right? And so then the utility function jumps in and says, all right, well, how well did I do? How happy will I as an agent be in that state? What's its utility value? Okay, if I make that decision on the world based off of what I know the current state to be, how the world can change, how my action can impact that environment, right? The current state of the environment. Okay, what that will look like, let me evaluate it. What's its utility? Okay, and then that can drive what action I should do at this point. Okay. All right. And then you can do that for all the different types of actions that are possible from that state that the agent found itself in. All right. So let's talk a little bit about learning agents, and we'll wrap this up. Okay. So agents. I mean, how does an agent get manufactured? How does it get created? How does it come into being? Well, a programmer. One thing that you might be thinking of, or what's probably the most, what seems like the most obvious, is that some programmer, some designer, some engineer, has to program the agent. Okay, and programming agents, their intelligence can be painful. I mean, it can be laborious. I mean, think about if it's a table-based agent. Think about how huge that table must be. Think if it's a reflex agent, right? Even if it's a simple reflex agent, think about how you have to program all the if-else rules or all the if-then rules, right? If it's a model-based agent, you have to program in its knowledge of the physics of the environment in which it finds itself, and so on, right? So remember Alan Turing? Talked about him and the history of AI. He said, you know what? That sucks. He said, here's what we should do instead. Okay, we should focus on building machines that can learn, right? What we should focus on are algorithms that enable a machine to learn stuff, okay? And so then what you can do is you can let that machine learn, and therefore kind of maybe think of it as programming itself to act within its environment. Started off with a simple set of rules, and then you focused on teaching it how to learn based off of those rules, and then as it perceives more things about its environment, it evaluates how it did with a particular decision, then in the future it can decide how better to behave. Okay? And a lot of times this is a better way of doing it. Okay, so what is involved in a learning agent. Okay, so here's some components. Okay, now you still got your sensors, right? Because that agent has to be able to perceive its environment. You still have your actuators because it has to be able to act upon its environment, change its environment. Okay, but there's some new stuff here. Okay, so there is a critic, right? And the critic component is basically saying, huh, that was a good decision. That was a bad decision, right? So based off of a decision that the agent makes, there's a critic subcomponent that says, oh yeah, that was good. Oh yeah, that was bad. Okay, so it gives feedback to itself, right? It's its own little voice. It's introspective. It says, oh well, that decision wasn't so good. Well, this decision was so good. Then you have a learning subcomponent, which has the ability to learn from past decisions, right? To take into consideration the feedback from the critic and learn, yeah, that was bad, or no, that was good. So I need to maybe change what I do in the future. Okay. Now the performance element here is what we had been thinking of as the agent function before, right? So imagine if you added a bunch of supporting elements to your agent function, therefore your agent program, right? That has the ability to modify on the fly your agent program, right? So these subsystems, critic, learning element, problem generator, more on that in a second, have the ability to directly or indirectly change the agent program, okay, update it. And so based off of what's learned, based off of what the critic is, and in addition, it has a subsystem or a subcomponent called the problem generator. And what the problem generator does is it kind of goes through a bunch of what if scenarios based off of what the agent understands about the environment in which it behaves, its actions it can perform, and so on, right? So you can have the critic part, which evaluates the decisions the agents have made. You have a learning element, which learns from the feedback, changing the main agent program, that thing we've been talking about so far. And that agent program can, let the learning element know, okay, well, this is what I know about the world, this is what my actions can be, and all that sort of thing. And then you have a problem generator that just goes through a bunch of what if scenarios. Right? And those what if scenarios, before the agent ever encounters them in the environment, can update the performance element, the agent program, to say, okay, go ahead and let's go ahead and do this. If you ever encounter this situation, do this. Okay, here's something I thought of. This is what you really want to do. So problem generator can be, think of it as like wargaming, where it's just going through all these possible scenarios and say, okay, what if we encounter this? What if we encounter that? What if we encounter the other thing? Oh, you know what? Based off of that, hey, agent program, main performance element, which was the agent program we were talking about before, this is how you should behave. This would be the best thing. Okay? And then the critic, again, is, I'm repeating myself, I'll move on, okay? So hopefully you get the idea of what these pieces are for. So let me just summarize them for you. The learning element's tasked with making improvements. Performance element, tasked for choosing actions. And again, this is what we had thought of as being the entire agent before. Critic, that's letting the agent know, hey, this is how you did. Okay? And the problem generator, hey, based off of these scenarios I'm running through my head, here's what you can do in the future. Okay, let's think it through. So go back to that taxi example. Okay, so a taxi has to try to make it through an intersection, okay, safely, right? So the performance element, okay, has to decide how to do that, right? What's the actions that I have to take to make it through there? Oh, and I almost forgot to mention, right, the performance standard, right? So, you have some standard that you as the designer have to impose upon it, so that way the critic has some standard by which to criticize the agent, right? There's some kind of standard that you have to impart, that you have to come up with, that the critic uses to criticize itself, okay? That it uses to criticize decisions. All right, so the taxi makes a decision. Okay, the performance element makes the decision, says, all right, let's go into the intersection. Now the critic subcomponent could see, part of our percept sequence was that other drivers in the intersection were giving us various types of sign language, if you know what I mean. You know, letting their negative feelings be known. Well, in that case, the critic is saying, no, that was bad, right? That was a bad, bad, bad choice. That didn't work out very well. So the learning element then says, all right, well, let me come up with some new rule. Let me modify the behavior so that way we don't do that again. Okay? And then the problem generator then can come along and say, all right, well then let's come up with some scenarios in the future that we can test those rules against. How are we going to handle that in the future? Right? So the performance element made a decision, tried to go through the intersection. The agent observed the negative reactions from other drivers. The critic said, bad. Learning element said, all right, well, let's try a new rule so that way we avoid bad. And then the problem generator said, okay, let's run through that in our head. How's that going to play out? Let's test that rule. Okay? All right. So utility agents, they can use external evaluations, right? So they can use an external performance metric, some other entity outside of itself that tells the agent bad, good, bad, bad, good. So if that happens, then that feedback from that external evaluation agent, maybe a second agent, right? It's telling it external to itself. Then that information becomes a percept, right? So the agent tries to do something, and then it looks and says, "How'd I do? How'd I do? How'd I do?" Think about a child and the parent, and then that external agent, that parent says, "Bad." Okay, and so that's a percept. Okay, and so that's a reward or a penalty, and so the reward means, okay, yeah, I did good. Then I'm going to make that decision in the future. Okay, penalty means let's not make that decision in the future. Right? So the evaluation can come as or from an external source. Okay, and the individual evaluations are a percept, and they're good or they're bad, and then based off of good or bad, modify your future behavior. Okay, so to summarize, agents that are intelligent, they have these different components, and they're constantly going through and modifying or going through a process of modification so that each one of those components arrives or converges on a certain point, and that certain point is a better decision for the future. So that way, that leads to better decisions, which leads to the agent ending up in better states. Okay? All right, so hopefully I didn't lose you there. Hopefully my explanation was okay. Again, if you're having problems with that, let me know. Okay, give me a holler, stop by my office hours. Be happy to walk through it with you. And also, hop on the textbook, right? Skim through the actual text. If it wasn't as clear, that might be the easiest thing to do, because this chapter especially, it's pretty easy. Okay. In terms of reading, I'm not saying in terms of understanding, or whatever. It's going to take some work to pull it all together, but the text itself for this chapter is pretty good. All right, so how the different components work. All right, so those different components. Now this is talking about how an agent's environment can be represented. Okay, so internally, think about memory, think about data structures, think about variables, think about that sort of thing, right? How could you write a Python program where you could represent an environment? I think very practical terms. Okay, or how would you write a C++ program to represent something? The tic-tac-toe board could be part of the environment, right? X's and O's are arranged in a certain order. Or think about in a first-person shooter. You've got the player, and you've got an AI bot in particular positions in the game world at a particular instance of time. So programmatically, how do you represent that? Okay, so the components can represent an environment, there's three general approaches: atomic, factored, and structured. Okay, and um, they're kind of on a scale in that they go from the most simple, most restrictive to the most complex and most flexible. Okay, so atomic is the simplest, easiest, but I guess you could say least um, complex, least useful, right? Least possible application. That's atomic. Structured is the most complex, the most broad application, and then factored is kind of like in the middle. Okay. So here's some graphics, kind of give you an idea of this. So what's an atomic representation of the of an environment? So you can imagine a very simple map, right? And you're trying to represent the location of a car or the agent in some city, right? So an agent is either in um, Concord or it's not. It's either in San Francisco or it's not, right? It's either in Nevada or it's not, okay? It can be in Nevada or it can be in Arizona, but it can't be in both, right? And the relationship between the states doesn't matter. I'm here or I'm there. A, B, that's it. Or on the graphic here, B, C, that's it. So it either is or it isn't there. True or false, Boolean. Okay? So that's an example of atomic. Now a factored representation of an environment isn't just Boolean. Okay? It allows for a little bit more granularity than that, right? You might have several individual pieces of information that describe that environment that have to be represented. So imagine the tic-tac-toe board, right? It's not just on or off. There's a board or there's not, right? It's more complex than that because you have to keep track of where the X's and the O's are, right? So it's not good enough just to have a single Boolean variable. You know, it is true that that this agent is Oregon, or it's false that it's in Oregon, right? Tic-tac-toe board, you've got 9 squares, right? So you got 9 different values that you have to keep track of, okay? And each one of those squares could have 3 different possible values in those squares, X, O, or blank, right? So that's way more complex than just that atomic representation. Okay, now, so a combination of variables, I guess you could say. Okay, it might be that you need to create a struct, right? So, or a class to represent this, a single class to represent a state, a couple variables, list, that sort of thing, a vector. Okay, now a structured representation of an environment would include all of those things. It can do everything that atomic can, it can do everything that factored can, but in addition to that, it also allows for including or incorporating relationships between different entities, right? So a structured representation is what you would need, maybe for something like an MMO, right? Where not only are you saying that this player is here, this player is here, this player is here, this player is here, but also you might have to describe the relationship between those players. These 2 players are on a team, these 2 players are on a team. Okay, so they're related to each other because they're on a team. But also there's another relationship. This team and this team are enemies, right? And they're in conflict. Okay, and so then how's friendly fire play into that? Okay, and those relationships could change. Maybe the relationships are dynamic. So that's what a structured representation of an environment is dealing with. Okay, so anything that atomic can do, structured can do, anything that atomic can do, factored can do, right? But an atomic representation cannot do what structured can do. It gets more complex, and it's a sliding scale from left to right in terms of granularity. Okay, any atomic or any environment that you could represent with an atomic structure, you could also represent with a factored and a structured. Okay, but any environment that requires a structured um, representation cannot be represented with an atomic representation. It doesn't work in both ways. Okay, so let me just go through these really quick. Atomic representation, world states, indivisible. So these are algorithms that work with atomic representations. Search algorithms, game playing algorithms, hidden Markov models, Markov decision processes. So we are going to look at these two for sure. So search algorithms are in chapter 3. Game playing is chapter 5. Chapter 4 also there's some search algorithms. Okay, so very granular, not smooth. Factored, you got variables or attributes. Each one of those can have different values, as I was saying. Factored representations are the basis for propositional logic, which we will definitely get to. Bayesian networks, which I hope to get to. Machine learning, which we have a whole separate class on now at CSUEB. Let's see here. And with a factored representation, again, relationships. It's not very conducive to establishing relationships. Okay. Let's see here. And structured representation. This one is the one that you use when you have to talk about relationships, between different objects, between different agents. And so this type of representation is what you got for relational databases, first order logic, which is, I guess you could say, a higher form of logic than propositional logic. Different types of probability models, natural language processing, knowledge-based learning, right? So more complex, more flexible, more stuff you can do with structured representation. Atomic, simplest, very limited, very constricting, and then factored's in between. All right. So yeah, that's it. So there we go. Sorry, I wanted to get done faster, but I just can't shut up. So sorry about that. So let me summarize. Chapter 2. Agents. What do? They're in an environment. They perceive that environment, and they try to act on that environment to modify that environment. So the individual elements that you can perceive, or the individual instances of perceiving something environment, that's a percept. Okay. The items or the things that can change the environment, those are actions. So the agent function, which you write code for to implement, that code that you write, the implementation of that function is the agent program. And so all that's doing is mapping percept to action. Okay, now that form of mapping can be very simple in terms of a simple reflexive agent where it's just purely instinctual. I perceive, I do. Right? Or it can be a lot more sophisticated than that. Right? You can throw goals into that. You can take into consideration your understanding of the world. By you I mean the agent, right? Measuring potential outcomes, the utilities of different outcomes, of different states that will result from the action that the agent takes. Okay, so performance measures, those help to evaluate how well the agent did, its decision-making process. Rational agents are trying to maximize the expected performance measure value. Okay, it's not possible to make a perfect agent, but it is possible to make one that's rational, one that tries to make the best decision it can given the information that it has at that instance in time. They're not omniscient. They can't know the outcome of actions ahead of time. Okay, task environments, we talked about those. Remember P's, what does that stand for? Performance measure, environment, actuators, and sensors. So P's helps you to describe what you're trying to do, right? They guide how you're going to create that agent function, because you have to specify, well, how do we evaluate its performance? What environment is the agent going to be operating in? How does it impact its environment? How does it perceive its environment? So you just think these things through. P's, start with P's, okay? You need to deal with understanding the environment first. You want to specify that first. Remember, we went through different categories of how you can specify that, because that's going to, once you understand the environment, then that's going to explain to you or drive let you know what actuators you need to impact that environment, and also what sensors you need to perceive that environment, and then also how to craft a performance measure to measure how well your agent is performing within that environment. So task environments, they vary, right? It's infinite, right? The possibilities, they could be virtual, they could be real. Remember, we went through these different categories. Are they fully or partially observable? Is there one agent, or is there a bunch of agents acting? Is it deterministic, or is there some randomness in there? In other words, is it stochastic, episodic, or sequential? Do you only ever take into consideration one particular percept, or do you remember all the percepts that led up to this particular instance of time? Static or dynamic? Does the environment change while the agent's making a decision, or does it not? Discrete or continuous? Remember, that's talking about time, right? And we talked about whether or not something could be, some combination of the two. In terms of static or dynamic, sorry. So discrete or continuous, is time flowing smoothly, or is it, these discrete events in time? Okay, and remember this, when you're using this language to describe the environments, three different people might make three different arguments for how best to describe the environment. You try it out, you design an agent, you see if it holds up within your description. If not, then you go back and you refine your understanding of the environment, then you make changes to the agent accordingly. It's a trial and error process, just like any type of software engineering. And then finally, we talked about whether the environment was known or unknown, right? So it's really, really, really important to do your best to nail down the environment that the agent is operating in, because that's going to drive your decision as to what type of agent you need, and how it's going to perceive that environment, how it's going to impact the environment. All right, so agent programs are implementations of the agent functions, and the agent functions provide a mapping between percept and action. Lots of different designs as we went through, with different benefits and drawbacks. So simple reflex agents, those are the simplest, the easiest, and also the most limited. Model-based reflex agents are keeping track of the world as it understands it and as it has experienced it. It's not just looking at this percept, forget everything else, right? It's not just I perceive something, automatically do something. It takes into consideration what it knows about how the world behaves, the physics of the world, and maybe what it's experienced up to that point, what it's learned about the environment up to that point. Utility-based agents, they try to maximize happiness. Well, what does happiness mean? It's trying to get the agent to a state that is has the best utility, right? Has the best outcome based off of some measure. Okay, and all agents can improve through learning. So we talked about agents that have this ability to learn. We talked about the four different components, right? The critic, the problem generator, the learning component, etc. Okay, so that's that. You should be ready now to get started on your next homework assignment, and that homework assignment is going to ask you to design an agent. So to do it, I'll just remind you, use P's to describe the environment. Okay, remember where we saw some examples of P's. Let me go back and find it. Where are you? P's. Right, so here you go. So you can refer back to this to give you an idea. Now here's the thing, right? I mean, you're going to need to give me a little bit more information than just purity, yield, and safety. I mean, you're going to have to describe that a little bit more, because I don't know what you mean by purity. One word isn't enough. When I went through and I gave you an example of the part picking robot, I described what each of these little pieces meant, right? You kind of need to do that in the assignments in that way. You can't just say, performance measure, dog. Right? If I look at that and I go, what the hell is a dog? Then you're in trouble. You're gonna lose points, right? That's not really describing the environment. But remember, performance measure, environment, actuators, sensors. So a brief sentence just saying, oh well, purity. This is going to be the purity of whatever thing is being refined, right? Because this is a refinery controller. The purity of the oil, or something like that, right? The environment in which it's operating in. There's a conveyor belt, and the parts travel down the conveyor belt, and then there's these bins that the parts get sorted into, right? You can just give me a couple sentences like that, and so on. You can't just give me a one-word answer. You got to tell me what the hell that word is, right? And so then the properties of the task environments, you're describing the environment, and you're going through and you're telling me, well, it's partially observable because, or it's a single agent because, it's stochastic because, and two different people might have different reasons for saying it's episodic or static, right? Make sure that you give a reason. Don't just say episodic. See, like, this is good to refer back to give you an example of, or to get your brain thinking. But here it says crossword puzzle fully, right? Now remember when I was talking about this in the previous video, I said, well, it's fully observable because look, you can see the crossword puzzle and you can see the words that have been written in. You kind of got to tell me that in the homework assignment too, okay? So in terms of defining the agent function, feel free to use a table if you want, okay? You can look something like this, refer back to figure 2.3. Or you can do something like, let me see, move forward here. You could do something like this, right? Where you're just doing a bunch of if, else, if statements. You could do that too, right? That'll be fine. Let's see here. And make sure that I understand what it is that you're talking about, right? So when it says here, status equals dirty, well, I described that to you when I talked about the toy problem. And in the homework assignment, talks about the environment in general terms, and so you can just refer back to that and it should be fine. All right, so I think that's everything. Like I said, as usual, if you have any questions about anything, shoot me an email. Expect an answer within 24 hours, and also feel free to to stop by my office hours, hop on Blackboard. That's what I was trying to say, and with any questions you might have, and I'll do my best to get those answered for you. Remember, I'm at your service, right? So don't hesitate to reach out. I'm here for you, okay? All right, we'll see you in chapter 3.